Hello, everybody. Mr. Hayes here again. So, last time we talked about the difference between heat, thermal energy, and temperature. Remember, temperature is the average kinetic energy of a substance, whereas thermal energy is the sum of that kinetic energy and potential energy of that substance. Finally, heat is the transfer of that energy. So, we talked about how heat transfers through conduction, convection, or radiation. Now, every substance heats up slightly differently. We say that different substances have a different specific heat. So, specific heat is the amount of energy required, and we're going to talk about it in metric, although you could switch these units with any other units, to raise 1 kilogram of a substance 1 Kelvin. Now, you could also say 1 degree Celsius because raising by 1 Kelvin is the same as raising by 1 degree Celsius. The units that we list specific heats in are joules per kilogram Kelvin. Every substance has its own specific heat based on the composition of its particles and their properties. For instance, aluminum has a specific heat of 897 joules per kilogram Kelvin, which means it would take 897 joules of heat to raise 1 kilogram of aluminum 1 degree Celsius or 1 Kelvin in temperature. Water, on the other hand, has a specific heat of 4,180 joules per kilogram Kelvin. Now, water, we're talking about liquid water there. Ice actually has a specific heat of 2,060, whereas water vapor has and this is kind of interesting. Ice is 2060, whereas water vapor is 2020. Ice or liquid water is actually much higher than either one of those, which is kind of interesting. And that has to do with the chemical composition of water and how those type of what we call hydrogen bonds work in that particular substance. So we can measure heat. The variable we use for heat is a Q, and it's an energy transfer. So let's look at what the units would be here. The formula we're going to have is we're going to take a specific heat and multiply it by mass. We're going to have mass times specific heat times a change in temperature. So let's make sure we're clear on these. This is mass. C is what we use to represent specific heat of the substance. So every substance will have its own specific heat, and that either needs to be gotten from the problem or from a reference material. You might memorize a few, but it's not something you work out on the spot. You need to reference that somewhere or solve for it. And delta T is your change in temperature. And Q is the measure of heat, which remember is a transfer of energy. So what would our units for heat be? Mass is measured in kilograms. Specific heat is joules per kilogram Kelvin. And if we're doing a change in temperature, that's going to be measured in Kelvin. So simplifying this out, we get that our heat would be measured in joules, which makes sense because it is a transfer of energy. So let's do a couple problems using that formula for measuring heat. All right. So let's use examples of the heat formula here. So this is Q equals MC, C being the specific heat, times delta T. So let's do a very straightforward one to start with. Let's say that we are heating a sample, a 450.0 gram sample of copper. Use the abbreviation Cu from chemistry. with specific heat, copper has a specific heat of 385 joules per kilogram Kelvin. And the sample goes from 72 degrees Celsius to 94 degrees Celsius. So I know that our specific heat's listed in Kelvin, but the relationship between degrees Celsius and Kelvin is one of adding. So the difference would be the same. So we work this out. Our formula here is going to be Q equals 450 grams, but we're measuring our mass in kilograms for this specific example. So we're going to go with 0.4500 times the specific heat, 385, times the difference. We can just do the subtraction in our problem, 94 minus 72. We're going to be limited to 2 sig figs because of our temperatures, and we do that calculation. We get, with appropriate sig figs, 3,800 joules. All right, on to our second example. And we'll choose to do this in what I think is probably the most complicated way possible. You can do these a lot of different ways. Basically, when you have this having 1, 2, 3, and this is really 4 and 5 variables because you have your starting temperature and ending temperature. The basic process is if you know 4 of those pieces of information, you can find the 5th. All right. So another one we could do is if we impart 4,550 joules of energy into 2.00 kilograms of water to raise the temperature from 10.0 degrees Celsius, what is our final temp? So using the formula, we're going to start, our heat would be 4,550 because that's how many joules of heat we are imparting. Mass is 2.00. The specific heat of water, there is a page in your book, page 325, where you can look that up. I think most problems will give those. But water has a specific heat of 4,180. We know that our starting temperature is 10 degrees Celsius, but we don't know what our final temperature is. So I'm going to say TF minus 10.0. Now, we've also had equations like this before. You have a couple options. What you could do is you could multiply 2 times 4,180, distribute, and solve that way. Or you can divide those things off at the beginning and then add 10. Either way is sufficient. And to our limit of 3 sig figs, we're going to get that T sub F equals 10.5 degrees Celsius. So all that energy didn't do much. So let's compare that to the copper example. We have about half a kilogram of copper, and because it has such a low specific heat, 3,800 joules of heat gave us an increase in temperature of 22 degrees. But because liquid water has such a high, we did have more mass here too, but has such a high specific heat, having 4,550 joules only raised it about half a degree Celsius. All right, next topic. All right, so how do we measure specific heat? Well, there's a process that we do experimentally. So to discuss that process, we're going to have to discuss a couple things. The first thing is that we have to know the specific heat of at least one substance. And so when all this was started, they dictated a specific heat of purified water. Now, we're going to use something called a calorimeter when we talk about these thought experiments. What a calorimeter is a calorimeter is a very good insulator with specific properties. So, those properties are that it is a closed container because we want a closed system. Usually the calorimeter will have water in it. And the purpose of the water is to serve as kind of our baseline of comparison. Oftentimes there'll be a stir rod, but there's always a thermometer that's stuck in the calorimeter. And it's always sealed really, really well because you don't want any of that heat to escape. You want as little heat transfer out as possible. So basically, to measure the difference in the specific heat of something, you have to then use a substance that you know the way the heat's going to transfer out of that substance into the substance you want to test. So you have a test substance in there, and then the water serves as your control. And basically, the heat will transfer out of the material into the water. And because we know water's information, we can figure out how much heat transferred out of that water. We also need to know the mass of our sample and various other pieces of information so we can kind of control and figure out exactly how much thermal energy came out of it. So let's look at a real quick example. Let's say that we have a 1.55 kilogram sample of metal. We don't know what that metal is. We're looking for its specific heat. This is actually a way that they can use to identify certain types of metal is through their specific heats. So, if we have, let's say we have actually let's do 10.0 kilograms of water. Oh, that's way too high. So we'll go with 5.00 kilograms of water. Initially at 12.0 degrees Celsius. And we place the metal at 74 degrees Celsius. We want to find the specific heat if the system ends. System not ends, but equalizes, reaches equilibrium at 22.0 degrees Celsius. So what we do is we heat this up. Now, how do you control the temperature of the object? Well, a lot of times what you do is you'll get a sample of water at a very specific temperature, and then you'll immerse the metal in that water at that temperature for a very, very, very long time, knowing that it's picked up all the thermal energy, like a preposterously long time, to ensure that it's achieved maximum conversion to that thermal energy. And then you basically see how much of that energy transfers out into the water and changes that water's specific heat. So the basic idea here is that the heat of the metal is going to be the heat absorbed by the water. So the heat given off by the metal is going to equal the heat absorbed by the water. So we're going to have two equations here. The first one is going to be the heat of the metal. Well, we have a 1.55 kilogram sample that we don't know the specific heat of. and it is going to go from 74 degrees down to 22 degrees. Now I should say that one of these is going to come out negative and one of them is going to be positive, because one's loss, the metal's loss, is going to be the water's gain. So we got to keep that in mind. Is going to equal the amount of water, 5.00. Now we have to know the specific heat of water, which we used last time, and that is 4180. And the water is going to go from 12 to 22, so that's a delta of 10.0. So you can work out the right, solve for the C on the left, and you will get, sorry, that should be negative 10 in there because it went up. And I got a specific heat of 2593.05. With sig figs, we're going to go with, let's see, what do we have here? 3, it looks like. Oh, no, metal at 74 degrees Celsius, so that's 2. So that's going to be 2,600. And the unit for this is joules per kilogram Kelvin, or joules per kilogram degrees Celsius. So that covers the two major types of problems. The first one being using that heat formula in a sense by itself, and then the second one is understanding how calorimetry works by understanding how one has to equal the other. All right, that wraps up section 12. See you guys next time.